All right, folks, so let's get started. We're going to finish up chapter 6, this half a slide, looking at valence electrons. So we're looking at the highest energy electrons on an atom. So we're kind of applying that knowledge of quantum numbers and actually putting electrons in orbitals in those boxes. So depending on the full electron configuration that you write for an atom, we can identify what are the highest energy electrons, because those are the electrons that participate in chemical reactivity, and we'll look into more details about that in chapter 7. Okay, are we paying attention? All right, okay. So we looked at some examples for main group elements, meaning S and P block elements. The number of valence electrons is the group number. Right? There's a meaning here with the group number. If you count up the highest energy electrons, if you write out the electron configuration, the highest energy electrons are in the highest N value. So for the main group elements, S and P, it's super easy. It's just it's group number. And we see that example here. Magnesium is in group 2A. There's 2 electrons in its S orbital. So 2 valence electrons. Carbon has 4. Because we have S and P, but then it gets a little weird for heavier elements here, like tin. Tin, if we write out the full electron configuration, you see that we include this 4D10. It's completely filled, but recall the rule here. We only count electrons from the highest N value. So does 4D, is that part of the highest N? No. So we do not count those 4D electrons. We only count the 5S and 5P, but then it still follows our rule, right? That how many valence electrons? 4 valence electrons, because tin is in group 4A. So, but remember, we're not counting those D electrons for those main groups. But then for our transition metals, it gets a little weird. Okay, so for transition metals that are kind of more on the left side, so like scandium through manganese, those lighter transition metals, we'd actually do pick or count those D electrons when we write out their electron configuration. So for example, scandium, if you write out its electron configuration as 4s2, 3d1, that D electron actually does count. And the reasoning is that your 4s and your 3d subshells are so close in energy. They're so close that we fill them up in the opposite order, right? And so as we're filling up a few of those D electrons, they're actually high in energy. And so we count them as valence electrons. So what we see for scandium, there's 3 valence electrons for scandium because we pick the D electron off of there. So oftentimes we will see those 3 valence electrons being lost. So we can see scandium 3 plus cations. Same thing for chromium. When we write out the electron configuration, we count those 5 3D electrons. So there are actually 6 valence electrons on chromium. Oftentimes, chromium will lose all 6 of its electrons, and we see chromium 6 plus cations as well. And so that's kind of an observation proving that there are 6 valence electrons on chromium, that those D electrons count because they're higher in energy. So what's common with these 2 examples is that D subshell is not completely filled yet. Once you completely fill a D shell, you have 10 electrons in one subshell, and what it does is stabilize that whole subshell. So once you completely fill that D shell, it is no longer high in energy and no longer is part of our valence electron count. So let me show you some examples here. So copper, if we write out the electron configuration for copper, it's one of our anomalous electron configurations. So it is argon 4s1, 3d10, right? It's one of the anomalous ones where it should be 3d9, but one of those s electrons jumped ship to the D shell to make it completely filled. So copper is interesting. It typically we see copper plus and copper 2 plus. So copper is weird and it's harder to see, but copper actually has 2 valence electrons here. It's not completely clear not why, but it's not as clear cut as our other examples where it's the highest energy electrons. And this is kind of the reason why transition metals are really weird. So copper in this case is kind of an off case, but these other ones, zinc and nickel, are a little bit clearer. So let me show you these ones. So zinc, if we look at zinc, is argon 4s2 3d10. Do we recall from chapter 2, or maybe 3, I forget, what is the common charge of a zinc ion? 2+. Is it sometimes 2+, or is it always 2+? Always 2+. It's one of our fixed cation charges. So just imagine, what 2 electrons are being lost to make a zinc 2+ cation? Which electrons do you think are being lost? The 4s electrons or the 3d electrons? 4s, because they are highest in energy here. So for zinc, because that 3d shell is completely filled, we don't count those in our valence electrons count. We actually just count 4s. So this actually has 2 valence electrons, right? And that's why we often we always see zinc 2+. We never see zinc lose its d electrons because it's too stable in energy. And then copper is an anomalous one. We will never ask you how many valence electrons are in copper because it's harder to predict. I actually shouldn't have included that example on this slide. I realized that while I was talking. So then let's just also look at nickel as well, because it'll kind of just complete the thought here. So nickel, if we write out the electron configuration for nickel, is argon 4s2 3d8. We oftentimes also see nickel 2+. All right, and so the same idea here is that, partially filled 3D shell. It's more filled than our other examples like scandium or titanium, that we actually don't include those d electrons in our valence electron count. This has 2 valence electrons, and it actually comes from the 4s electrons. So we kind of go back to the idea of following the rule. The highest n electrons count as valence. So if we look at, do I have a periodic table? So if you look at your periodic table, something like titanium, if we look at titanium, it's the second element in on our D block. How many valence electrons do we think are on titanium? Because it's an early D block element. It's kind of early. Is there 2 or is there 4? 4. And oftentimes we will see, if you remember naming, oftentimes you would see titanium 4 oxide. And things like that. So titanium 4 is common. But as you get heavier and heavier, or something like silver, its electron configuration is 5s1, 4d10. So it only actually loses 1 valence electron coming from the 5s orbital. That's why we see silver plus as the only cation that we predict from that transition metal. So yeah, transition metals are a little bit weird. But in the general case is that we're always looking at the highest energy electrons. Those are our valence electrons. And most of the time, at least for main group elements, it's just whatever group it's in. All right, so that's it. So that's chapter 6. You should be able to do everything for that homework. There really wasn't much information there left to do. So we do midterm review now, right? Right? Did you see my announcement? So download the announcement thing. Yeah. Sorry, I can't hear you. They are the ones in the s orbital. So those ones are lost first. Yes, because the way we fill electrons is not quite the same as when we take away electrons, and we'll learn that in chapter 7 when we talk about ionization energies. All right, so midterm review. So I submitted an in-class midterm packet just for, easy working on practice problems today. What chapter do we want to work on? 4, 5, 6? 5? 5, okay. Well, I already have it up. Okay, so 5 was thermochemistry. 5 was thermochemistry. We'll do a little bit of everything. And remember, I have more problems coming tonight during the Zoom review. All right, guys, do you want to review or not? Okay, yes, all right. So thermochemistry, so it's application of energy, understanding how energy is being transferred between system and surroundings. Remember, 9 times out of 10, you are not the system, you are the surroundings. What you observe, if you feel heat coming from a reaction, the system or the reaction is losing heat, you're gaining the heat. So that's actually a negative value of energy there, not positive, even though you're feeling like an increase of heat. All right, and that's like a common misconception. So we talk about different types of energy, potential, kinetic, internal energy, and we talk about heat and work, and that's a way to measure internal energy. So here in this question, we're looking at potential energy and how it increases. So potential energy and kinetic energy, we have two different equations for each of them. And that equation, even we don't have to actually calculate anything. We can use it to relate values to one another. What is the equation for potential energy? Do you remember? Yeah. Q1 times Q2 over D. So Q1 and Q2 represent what? Charges, right? The charges. So whether it's positive or negative, or like +1, -2, whatever, that's what Q1 and Q2 is. And D represents how far away they are from one another. So we can kind of make predictions based upon how those different terms change. We typically don't calculate potential energy. We typically ask you questions like, okay, if we change this about the system, how does potential energy change? So y'all remember our graph, right? And what it looks like. Hopefully it's like ingrained or at least tattooed on your body. So our graph looks like this, right? Where the top graph is what? Attractions or repulsions? Repulsions. So an example of a repulsion would be like what? Two negative charges, like two electrons, or two protons close to one another, so that's repulsions. All right, I'll make it electrons because we always talk about electrons. And then the bottom is attractions. So attractions could be like a nucleus and an electron because they're oppositely charged. So that means as distance, you bring them closer together, a nucleus and an electron, potential energy goes down, right? Because our x-axis here is d, or distance. So really, almost all of the answers here can be explained by this graph. So this question is saying, in which scenario does potential energy increase? So increasing going up here. So A, reducing the speed of a charged particle. Do we think that increases potential energy? Yes, no, no, why? That's kinetic energy. Speed is related to kinetic energy, 1/2 mv squared. And that's not what this question is asking, right? So this is kinetic energy, but just for fun, if we reduce the speed of kinetic energy, reduce the speed of a particle, will kinetic energy go up or down? Down, okay, very good. Yes, because you're just reducing V. All right, separating two negatively charged particles. So my thing here is identify, are you in repulsions or attractions? And then ask yourself, are you increasing D or decreasing D? And then you just look at the graph. So are we in attractions or repulsions? Repulsions, so we're at the top of the graph. So if we separate them, are we increasing D or decreasing D? Decreasing, so is potential energy going up or down? Down, we're going lower. So no, so B is no. All right, so yeah, repulsion, separating, so that means D goes up. All right, bringing two oppositely charged particles closer together. Are we in repulsions or attractions? Attraction, so the bottom graph, is D increasing or decreasing? Decreasing, we're bringing them together, so their distance is decreasing. So are we going up the graph or down the graph? Down, so is that correct? No, because we want potential energy to increase, become more positive. So it has to be D, right? Bringing two positively charged particles closer together. Positively charged, both of them, that's repulsions. D is decreasing, we're bringing them closer together, so we'll feel greater repulsion there. We're going up in potential energy. You'll actually feel it, right, if you think about two magnets. So the answer is D. See how I did that? I answered everything with the graph. If you have that graph in your mind forever, it can answer a lot of questions. Okay, so keep going. All right, let's calculate internal energy for this thing I drew. All right, I made it in PowerPoint a couple hours ago. So the equation we use for internal energy. Oh, so maybe I'll just quickly say internal energy, E, is the sum of all kinetic energy and potential energy of your system at a certain time. But chemists, we don't calculate that. We don't like to actually calculate. It's pretty much impossible to do so. Instead, we calculate the change in internal energy for a process, so a system undergoing some type of change. So that's what we're seeing here. We have a box, it's our system, and it's undergoing some type of internal energy change. So this should say change in internal energy, that's why I have the delta. So once we have the delta, change in internal energy, we don't have to think about kinetic energy and potential energy anymore. We can think about heat and work. Those are things that we can actually measure. Yay, people are getting their calculators out. So delta E equals what? Q plus W. So if you didn't put too much thought to this question, you might just add up the numbers 22 and 15. Right? That's what someone might do. But the signs here are really important. We have to understand, is the system gaining that much heat or is it losing that much heat? Is it doing that much work or is that much work done on it? So we have to get the signs right here, because if you just add these two numbers up, you'll be wrong. Okay, so let's see if we can't get the signs of heat. All right, and I try to show the arrows, right? The arrows to show where heat is going. So Q is heat, work is W. So based upon these arrows, is the system losing heat or gaining heat? Losing heat. So is Q positive or negative? Negative, yes, because the system is losing heat. So Q is negative 22 kilojoules. Okay, so if you remember, that's the system, and we, this is us. Okay, that's me. What we would observe is we would feel heat coming off. This is an exothermic reaction. All right, that's what we would feel. But remember, what we're focusing on is the system. The system is losing the heat. Okay, so work. Is the system doing work on the surroundings, or is the surroundings, so me, am I doing work on the system? I'm doing work on the system. So is work positive or negative? Positive, yes. So positive 15 kilojoules. All right, and that's what we add up. Did anyone just want to add up 22 and 15 and you thought that was the answer? It's never that simple, guys. It's never that simple. Okay. All right, and then whatever that answer is. Okay. I don't have a key for this because I just made it this morning. Okay. All right. So, okay, other ways we can think about thermochemistry. So thankfully, because we live on Earth and the pressure is always the same, we can think about energy changes of chemical reactions in terms of enthalpy. Enthalpy is basically just a heat measurement at constant pressure. All right, so instead of thinking about internal energy changes of reactions, we think about enthalpy changes of reactions instead. Still think of it as energy. So this reaction is showing some type of reaction happening, and it's telling you how the energy of the system is changing relative to products to reactants, how it's changing. So based upon the sign of delta H, you can just think of it as heat. It's a negative sign, so the reaction is losing energy. So what will we feel? We feel heat, so it's an exothermic reaction. So other than that, that detail about the direction of heat, how we kind of apply stoichiometry with thermochemistry is exactly the same as we've been doing in chapters 3 and 4, how stoichiometry works, right? Like if I say, if I react 1 mole of iron to chloride, and I ask you how many moles of chlorine gas reacts, what would you tell me? If 1 mole of iron 2 chloride reacts, how many moles of chlorine gas reacts? A half mole, right? So we still use this coefficient stoichiometry here. So the only thing we do is now use that heat term, right? So instead of saying 1 mole of this is half a mole of this, I can say 1 mole of that is this much heat. If I react 1 mole of iron 2 chloride, I will get 57 kilojoules of heat out. Exothermic. So the sign just tells me the direction it goes. All right. So this question is saying, let's calculate the amount of heat consumed when 3 moles of Cl2 is produced. So this reaction is showing iron 2 chloride plus chlorine gas gives us iron 3 chloride. So if we want to produce chlorine, do we want to do the forward reaction or the backwards reaction? The backwards reaction. Do I need a new reaction to figure that out? No, we can just, what can we do? Reverse the reaction. But if we reverse the reaction, what do we also need to do? Change delta H. So what you can do is you can rewrite it if you want. So iron Cl3, I'll just drop the states because I'm lazy. Iron Cl2 plus half a mole of chlorine. So I just reverse the reaction. And the new delta H value is positive 57 kilojoules. So this means that in this direction, the reaction is consuming heat in order to produce, right? And now we can actually answer the question. So we're starting with 3 moles of chlorine. So this is what's given, and we want to know how much heat is consumed. So the equality that we can write here is half a mole of chlorine gas equals 57 kilojoules of heat. So that's an equality I can use just like stoichiometry. Just like if I said something like 1-to-1 or 1-to-1/2, it doesn't matter. All right, and then we set it up. So 3 moles of chlorine gas. All right, so in my next step here, am I going to put the 57 kilojoules on the top or the bottom? Top. So 57 goes on top because we want to put the 1/2 mole on the bottom, chlorine gas. And that's it. So that's the answer. And so the detail here is what is the sign of heat? It's positive because it's being consumed. We're doing the reverse reaction. If the question would have said, calculate the amount of heat given off when 3 moles of chlorine is consumed or reacts, then we would still be doing the forward reaction, and we would have a negative sign of delta H. But the value would still be the same. It's just the sign is different. Okay, so that's stoichiometry. Like the simplest type of stoichiometry, really. Okay, keep going. So other ways we can talk about enthalpy and calculating it. We talked about calorimetry, bomb calorimetry, delta H is a formation, and we also talked about Hess's law. They're all basically based upon the same principles. Oh, and then bond enthalpies, all based upon the same principles that we can add and subtract reactions from one another, but we have to do the same thing to the enthalpy values. So here, I think I stole this question from Chegg. I've run out of questions. Guys, I give you guys so many questions. I've run out of them. Someone told me, they're like, we already did this question, Dr. N, in office hours. They're like, we've already seen this question, and I can't write anymore. So I had to steal it from the internet. All right, so here is a question. Calculate the enthalpy of this reaction. So this reaction is our target reaction, right? That we want to know the delta H of this. But we're given other puzzle pieces that have given delta H values. So I like to just kind of focus on one substance and make those given reactions match it. Does that make sense? Right? So in this case, I see like, okay, there's 2 NOs. NO, I look and see which reaction has NO in it. So right here, the second reaction does, but then I ask myself, is it on the right side? Is NO in the given reaction on the correct side? No, so what do? Reverse it. Is it in the right number? No, so then what do? Multiply. So total, we're going to take reaction 2. We are going to multiply by -1 and multiply by 2, right, to get it all good. So it'll be 2NO, arrow, so 2 times 1/2 is just 1, so N2 plus O2. But we have to do all those same things to the delta H value. All right, so the new delta H value would be -180.4. I think that's right. I'm not very good at math. All right, so what I like to do, if there's a substance that's in both reactions, so do you see how O2 is in both of them? Skip it. Skip it. Because if you try to make this one match, then you're just going to mess it up with the other one when you add the other one. So look at the things that only appear in one reaction. Does that make sense? So I'm going to look at NO2. I'm not going to try to balance O2. What I'm going to do is balance NO and NO2 and just pray that O2 cancels to the correct number I want. And most times it does. So I'm going to look at NO2 and look at what reaction has that. So it's right there. So NO2, is it on the right side? Yes. Is it in the right number? No. So all we have to do is just multiply reaction 1 by 2. All right, and so just rewrite it. So N2 plus O2, 2O2, there we go, equals 2 NO2, and then the new delta H value, that's multiplied by 2. So positive 6.4. All right, and then you can check your work and see what cancels. So N2s cancel, one of the oxygens cancel, right? And then, is that the reaction I want? Is that the target? Yes, it is. So just check your work, and then that means you just add up the delta H's. I like questions like this, and then it's whatever these two numbers added up are. All right? I don't know what the answers are. I don't have them. Okay. Good. All right. Okay. Calorimetry. Okay. Specific heat. Specific heat of octane. Just told folks this weekend I just bought a tractor, a diesel engine. Diesel is different than regular cars, and if this weren't the midterm review, I would explain the difference between diesel engines, because I don't know, remember on the first day of classes I told you, like, chemistry. I love chemistry because it gives me the tools to answer all questions that I have about everything, like why do only diesel engines roll coal? Okay, maybe I'll save it for some other time, all right? So you can ponder on that, because I just bought my first diesel engine and I can roll coal down my driveway at 5 miles per hour. Okay, all right, so octane, because octane related to regular gasoline in cars. All right, so I give you the specific heat there with the correct unit, joules per gram degree Celsius. So I'm asking you, how many kilojoules of heat is required to raise the temperature of a gallon of octane, and I tell you the mass, from this temperature to this temperature. So when we're dealing with specific heats and stuff, what equation do we use? MCAT. Q equals MCAT. But the C in MCAT is what? Is that heat capacity or specific heat? Specific heat, very good, yes. So Q equals MC subscript S delta T. If we were talking about heat capacity, it's Q equals just C, which is heat capacity delta T. And you can tell from the unit itself. So it's just plug and chug, right? So delta T is always T final minus T initial. So I don't know the answer to this. So the change in temperature, we're increasing the temperature by 73 degrees. I give you the mass, it's in kilograms, so that's 3.7 times 10 to the 3 grams, and then I just stick in that specific heat. So the amount of heat I need is, mass is 2.7 times 10 to the 3 grams, times specific heat, so 2.22 joules, gram K, times 73 degrees, so whatever that is. All right, oh, and then convert it to kilojoules. Okay, I'll just give you the answer. So 2.22 times 2.7 E3, so it's a really big number, and then to convert it to kilojoules, it's 430 something, 38 kilojoules is required. I don't know about sig figs. It's probably should be 2 sig figs. Yeah, it's 2 sig figs, okay. So with that number in mind, let's just kind of think about it. If we had equal mass, yes?
In the question, the specific heat is given in grams per Kelvin.
So why don't you try it? So when it's a delta T, it doesn't matter whether it's Kelvin or Celsius. So why don't you try to convert 22 to 95 degrees Celsius to Kelvin, and then take the difference. You'll see that it's the exact same number. So you don't take the difference value and then convert it to Kelvin. It doesn't work that way. You have to take the two values, convert them to Kelvin, then take the subtraction. And you'll prove to yourself that it's actually, when you take a delta difference of temperatures, Celsius and Kelvin are the exact same. Okay, all right, so without doing any calculations, which would require more energy to heat in this scenario? The same mass of octane or the same mass of water? Which one requires more energy? Don't do any calculations. Water, because specific heat is higher. The reason we're comparing specific heat is because we're comparing the same mass of sample. If we weren't comparing the same mass of sample, we would have to compare heat capacity. Okay, let's keep going. So, do we want to do a coffee calorimeter question? Oh, but they're so long. They're so long. Okay, but the nice thing, okay, so I'm going to tell you guys something. This question, it's the longest question, and there's a lot of places to go wrong. So if you don't have the time to learn how to do this, just skip it on the exam. Just skip it. All questions are weighted the exact same. Just skip it and spend time on things that you can do. This is a really tough question. Tons of tiny little things to go wrong. I'll tell you a story. I take the exam every year, right? And there's one year I took the exam, I got one question wrong. Guess one which one it was? It was this one. And you know why I got it wrong? It was a negative sign. That's why. I got the number right, but I just didn't put the negative sign there, all right? Okay. So, we are dissolving a salt in water, okay? We have calcium bromide, we're dissolving it in water, and we see the temperature of the water increase. So right off the bat, you can predict the sign of delta H, because that's what we're doing here, calculating the delta H of dissolution of this substance. So if the temperature of the water increases, is the dissolution process exothermic or endothermic? Exo, so delta H will have what sign? Negative. So this is what I should have done. If I would have taken the half second and thought about it, okay, I would have gotten the answer right. But I didn't, because I just forgot. All right, and I knew that the delta T was a positive, that it should have been exothermic, so delta H is negative. But I will point out, if this was a multiple choice question, and just by you thinking about it, you've eliminated half the options, right? Okay, all right, so let's actually do the question. So delta H, when we calculate it in any type of calorimetry, it's Q of the reaction over moles of the thing. So in this case, it's calcium bromide, right? So whenever we calculate delta H's for these things, we calculate how much heat is involved in the reaction, and then divide by the amount of moles of stuff that's reacting. So in this case, it's calcium bromide. So now we need to figure out what is Q reaction. So Q reaction, or negative Q reaction, what the reaction loses is equal to the Q of the solution, where Q equals MCAT. All right, but we have to think, what is the mass of the solution, what is the specific heat of the solution, and what is the delta T of the solution. Delta T is easy because they give it to us, right? They say that the temperature increases from 21.5 to 23.3, so it goes up a couple degrees. So delta T is final minus initial, so that is a positive 1.8 degrees Celsius, so that's delta T. Specific heat they give to us, it's the same as water, but this is what's often the most common mistake, other than the sign, is the mass that we use here. Do we use 120 grams? No, we use the sum of the water and the salt, so plus 1.67. So you have to add the mass of the salt that you're dissolving to, because everything in the cup increases in temperature. And so that tiny bit of salt does make a difference in your final answer. So the mass that we use in our Q equals MCAT is equal to 120 plus 1.67. So whatever that number is, 1 to 1.67 grams. That's the mass that we use. And so now it's just plug and chug. 121.67 times specific heat, so 4.184 joule, gram, Kelvin, or Celsius. It's the same number. It's the same exact number. And then times 1.8 degrees Celsius equals negative Q reaction. That negative sign has to be there. Has to be there. First law of thermodynamics, because what you get once you do the math calculations, you get that Q reaction is a negative number, right? And we need that because delta H is a negative number. So 121.67, that's grams. And so Q reaction has what unit? Do we know what unit? Kilojoules? Just joules. In this case, it's just joules. So we have to do a little bit more to get it into kilojoules. But because specific, because specific heat is in joules per gram Kelvin, the Q reaction is in joules. So this is 916.3 joules. Oh, sorry, negative. Yes. Whew. See, negative. All right, is that our answer? No. So we need to do two things. Convert it to kilojoules, but then also divide by the number of moles of calcium bromide that's there. So delta H reaction is negative 0.9163 kilojoules. Sorry, I just skipped a step to go from joules to kilojoules. And then we divide by the number of moles of calcium bromide. How do we get that? Yeah, we use what we started with, 1.67 grams, and then we use the molar mass that's given here, or you could have gotten it yourself. Divide by, because these two values can give us moles of substance, right? So there we go. So if I zoom out a little bit. So the bottom here, 1.67 grams, about 200 grams is 1 mole, right? And so grams cancel, so that's moles. So that's your answer. So divided by 1.67, divided by like 200, boop, 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 boop. Negative 109.7, I don't know. I just took this from the internet also. That's what I got. I don't know about sig figs. It should probably be 2 sig figs, right? So there's my answer. Wait, negative, right? So yeah, take the half second. Take the half second. Once you get your answer, check with, the observations you made. We just got a negative delta H. That means it's an exothermic reaction. So you would anticipate the water temperature to increase or decrease? Increase. Did that happen? Yes. So then we at least got the sign right. Okay. So with this question, it's super systematic. Like, you'll see all the examples I show in the overview sheets, blah, blah, blah. They all are exactly the same. I give you a mass of something, of a salt with a molar mass. I give you a temperature change, and I give you a mass of water. You have to add the masses to get mass of solution, and then you do all those steps. It's super systematic. But if you can't get it by tomorrow, I would just say skip the question. Is that fair? Okay. Because it is tough. It's tough. It's the one question I got wrong. Okay. All right. How do we feel about that? Good. How many people can do it? You can just like crank it out, right? Like you see it and you can just crank it out. But just, again, take the half second and check the sign, please. Please. Okay. All right. Let's move to a different chapter. Do you want to go to what chapter? 4. Okay. Let's do, can someone throw out a question number? 5. Okay, yeah. All right, so 5. We have sodium chloride and sodium sulfate. What's the concentration of sodium ions in the resulting solution? So the concentration of anything in molarity, so we're trying to find molarity of sodium plus. Molarity has the unit of what? Moles per liter. So specifically, it's moles of sodium. Yes, we want to figure out how many moles of sodium do we have over liters of the solution. Thankfully, we know the liters of the solution. It is 500. We're mixing two things together. We like double, or the new volume is 500 milliliters. All right, 500 milliliters or 0.5 liters. We need to figure out, okay, how many total moles of sodium plus are there in the solution? The problem is that there's 2 sources of sodium plus. You see that? So if we just figure out how many moles of sodium are coming from each of those substances, we just add them up and put them in the numerator. All right, so let's go through it. All right, so molarity, again, I always like to remind myself, 2.5 molarity NaCl means that there is 2.5 moles of NaCl in 1 liter. So if I start with 150 milliliters, which I'm just going to convert to liters right away, right? You see that? Okay. So that's of our sodium chloride. I can use that conversion factor I just came up with, so 1 liter on the bottom, 2.5 moles of NaCl on the top, and that will tell me how many moles of NaCl I have. So 0.15 times 2.5, so there's 0.375 moles of NaCl. So based upon the formula, can you tell me how many moles of sodium ion there are? It's the same number because there's just 1 sodium ion in that formula unit. So there's also 0.375 moles of sodium plus. So let's keep that in our back pocket because that's not the only thing in solution. We also have some sodium sulfate, but it's the same process, all right? So we have 350 milliliters, so 0.35 liters of sodium sulfate. So the molarity is 1 molarity, so that means that there's 1 mole of sodium sulfate in solution in 1 liter. So that's the, sorry, my sig figs are going away, 0.1 or 1.0 moles of sodium sulfate. So again, we use the conversion factor just like we did in the previous example here. This part right here was molarity, so we do the exact same thing. 1 liter on the bottom, 1.0 moles of sodium sulfate up there. But the problem is we need concentration of sodium ion. So we have to multiply the number we get by 2, because there's, for every 1, so if I actually want to do the like stoichiometry, or I guess it's not stoichiometry, but it's dimensional analysis, 1 mole of Na2SO4 is 2 moles of Na+. So don't forget that step. For every 1 unit of that salt, we actually get 2 sodium ions there. All right, and so if you do that in your calculator, 0.35 times 1 times 2. So there is 0.75 moles, no, just 0.7 moles of sodium plus coming from the other thing. So we just add those 2 numbers together, and that's our numerator. All right, so let's put this together. So if we go back to our equation over here, is my math right? 0.7 plus 0.375, those are moles of sodium plus over the new volume of the whole thing, so 0.5 liters, so whatever that is, plus 0.7375 divided by 0.5. Oh, I don't know. This calculator, I type too fast and it won't register. Did you get 2.15? Okay, cool. Do I go too slow? Did you all get it before me? Okay. All right. All right. Okay, other ones. Throw out some numbers. 6? 6. Okay, let's do 6. Okay, so we have a titration. What do we never use on a titration reaction, or a titration? Never use a dilution equation, ever. M1V1 equals M2V2. You never do it, okay? Promise me. Promise me, okay. All right, so we have a titration of a sample. 20 milliliters of a triprotic acid requires this much base to reach the endpoint. What is the concentration of this triprotic acid in molarity? So molarity equals what? Moles over liters. But for this sample, it's moles of the acid, specifically the triprotic acid, over liters. So maybe I should point out, triprotic acid means how many hydrogens are there? 3. So you can call it H3A, right? So we are trying to figure out, okay, how many moles of H3A do we have over liters of H3A? The cool thing is we know what the volume of H3A is. We know that. It's 20 milliliters. We need to find how many moles of H3A we started with that were originally in that 20 milliliter sample. So we're going to use the standardized sodium hydroxide that's given to us here, all right? So we kind of identified how many acids, how many hydrogens are on a triprotic acid. So based upon that, how many moles of sodium hydroxide are required to neutralize 1 mole of that acid, that triprotic acid? 3. So the equation, if we balanced it, it would be H3A plus 3 sodium hydroxides. Give us stuff. But we actually don't need to balance the whole thing. It doesn't matter. Because what we care about is this relationship, that 1 mole of H3A needs 3 moles of sodium hydroxide to neutralize it. Yeah? No, we do not. No, we do not. Because we want the molarity of the original sample, not of the base and the acid mixed together. We want the molarity of the original acid unadulterated. Does that make sense? Okay, all right. So we use to find moles, so actually we're going the opposite way, we're going this way. So to get moles of H3A, we will figure out how many moles of sodium hydroxide we delivered, and then use stoichiometry to figure out how many moles of acid are in there using the 1-to-3 ratio. So again, remember, molarity means 0.225 moles of sodium hydroxide equals 1 liter. So if we use 12.7 milliliters, convert that to liters, 1 liter, times 1 liter, 0.225 moles of sodium hydroxide. Okay. Oh, wait, sorry. So if we stop right there, we get moles of sodium hydroxide. But what we see here, this numerator, we want moles of acid. So this is where we use stoichiometry. Okay. So on the numerator here, the denominator, what value do we put down here? 3, just a 3? 3 moles of NaOH, yes, because that's what stoichiometry is. We want to cancel one type of substance, so 3 moles of NaOH, and then 1 mole of that triprotic acid is up top, H3A. And so you get that number, and you have how many moles of acid were in that container. There we go, times 0.225, divided by 3. Oh my gosh, I'm too fast. This calculate, it's too slow. Okay, and so what I get is 9.525 times 10 to the negative 4 moles of H3A. Is that my answer? No, that is our numerator. So now to be complete, we just divide this number we just got by 0.0200 liters. 0.02. Okay, so I get a concentration of 0.0476 molarity H3A. So on your own, you could change this question, just change the word triprotic to diprotic. And you could use the same exact numbers, but if you change it to diprotic, what changes in this calculation? The moles of NaOH. So instead of dividing by 3, we would divide by 2, but everything else stays the same. Okay? If this was a monoprotic acid, how would it change? It would just be 1 over 1. And again, it's all based upon that balanced chemical equation, because if you use M1V1 equals M2V2, you are ignoring that last step we did. 1 mole over 3 moles, you're not doing it. And that's why your answer might be off by a factor of whatever if you're doing M1V1 equals M2V2. So related to that, so we can use titrations here to calculate the concentrations of acids. So in this number 7, I just want to do it because it's like the same question. Instead of telling you, hey, you have a triprotic acid, and you start with this volume, what's the molarity? Instead, I give you a mass of triprotic acid, all right? And I want you to calculate the molar mass. It's the same question, I promise. We use the exact same process here. I ask you, what is the unit of molar mass? Grams per mole, right? So here, yeah, it's saying here we're titrating this much triprotic acid. It requires that much sodium hydroxide. It's the same numbers as the previous question. And it's asking, what is the molar mass of the triprotic acid? So just first thing off the bat, triprotic acid, it's H3A. Okay, so just remind you. But we want molar mass. So it's grams per mole. but it's not grams per mole of anything. It's grams of, if we're trying to find the molar mass of H3A, it's grams of H3A over moles of H3A. So let's zoom out. What do we already know of our sample? Do we know how many grams or how many moles we have? We already know the grams, so now we just need to figure out how many moles of H3A we have. Can I just kind of go up here? Can I go back up here? What did we do in this question? We found the moles, so that means we already actually have the moles because it's the same numbers. Okay, so you do the exact same thing. You start with, if this question, they give you mass instead of a volume, and you want to find the molar mass, you still do the same thing. Find moles of H3A, or the acid that you have. So you start with the standardized solution. So we're actually doing the exact same thing. Okay, so I'm just going to copy all this because I'm lazy. Right? Okay, so there we go. You start with the sodium hydroxide base molarity that we started with, and remember it's still a 3-to-1 ratio. If you use the balanced equation, it's the same reaction that's happening. It's just we're reacting it with a solid. So milliliters of sodium hydroxide, use the molarity of sodium hydroxide, and then you use the stoichiometry 3-to-1 to get moles of your triprotic acid. Now you have moles of H3A, and so then you just take it one more step. This number is your denominator, so 0.249 grams of H3A, because that was given in the question, over whatever number that is. So 9.525 times 10 to the negative 4. I don't even know if this it gives us a reasonable answer. I just made up numbers. 9.524. No, that's like a normal molar mass. Okay, so 261 grams per mole. Do we see how those two questions, 6 and 7, they're like pretty much the same? And so always what a question asks, if it's asking for, some unit, and tell yourself, what does that unit mean? What types of values am I trying to solve for? And so in this case, since we're talking about molar mass, we need grams of substance. We already have that. It was given over moles of substance. So this question is actually exactly the same. Not exactly the same. It's very similar. It's very similar, but we're just calculating something slightly different. Okay. Which one do you think's harder, the 6 or 7? 7? 6? They are the same thing. They're the same thing. So just be very cognizant of what the question is asking. All right. I have 3 minutes. Is there a quick question someone has? Something from chapter 6. Okay, yeah, let's do this one. The last one, 27. Okay. So this one's tough because students will often be like, oh yeah, it has to be C. C is not correct. But that's not what the question's asking. The question is asking specifically what violation is occurring. So we have to be aware whether a electron orbital diagram is correct, but also for, or if it's incorrect, but for what reason is it incorrect? So for this question, it says which diagram violates Pauli's exclusion principle. Do we recall what principle that is? No 4 quantum numbers the same, but in practice, what does that mean? If we have 2 electrons in the same orbital or the same box, they have to be opposite spin, because spin up is +1/2, spin down is -1/2. So which configuration, A, B, or C, or D, violates Pauli's exclusion principle? C. C. So be very cognizant of what the question is asking. So specifically, it would be this orbital, right? That we have 2 electrons. If you try to name both of those electrons, both of them are in n equals 2. Both of them have an L equals 1. Both of them are in the same, if we just say +1, 0, -1 m sub L. Both of them are in the same box, so they're both in the same ml, and they both have the same spin. That's why it violates Pauli's exclusion principle. All right. So then the second question here, how could we make this diagram correct? Could we make it correct? What quantum number do we have to change to make it correct? MS? Are you sure? Are you sure? So if we change ms, then we have this. Yeah, you need to spread them out, right? So what quantum number would we have to change about that one electron to make it go to a different box? ml, not ms. I think it's you want to say ms because that's the spin quantum number with Pauli's exclusion principle, but to make it completely correct, we actually change ml. Right, okay, so what's the second question? Which violates Hund's rule? A, yeah, so A. And then for which is the correct diagram? B, awesome. Okay, yeah. Oh yeah, actually D also violates Hund's rule. Yeah, so both of these, B and D, because in this, sorry, not B, B is the correct one. A and D. So A violates Hund's rule because we're not spreading them out. We're kind of isolating them in a pocket. D is also incorrect because we are spreading them out, but we're not making all the spins the same. All right, so once all the spins are the same, that's how we maximize a stable atom. I'll see you guys tonight at the review session. I will post the recording, yeah.
So why does C not violate Hund's rule too, like originally?
It also does, yeah,
Okay.
yeah. But I would say like that the Pauli's exclusion principle is the more important there.
Okay.
Where's Shane?
So for number 7,
Let's talk about that in office hours. Sorry.
like I know how to do it. It just doesn't give you the molar mass of HCl. So like, how do you do that without that? No, I mean I know we have it, but on the test I didn't think we were gonna have.
You always have a periodic table.
I know we have it, but I didn't think it looked it up.
Yeah, it does. It doesn't have names.
Okay, yeah. Okay.
Yes.
Will you post that key later
For what?
for what we just were doing?
No.
Okay. Just
I literally, you have so many resources.
I know.
Yeah, and
okay.
I literally
No
don't
worries.
have time.
I just
don't.
like that one.
You do? Well,
Yeah.
if you do them, and show me your work, I'll tell you if you're right
Okay,
or not.
cool.
Okay,
Yeah, maybe
yeah.
I'll do that and email you.
Yes, yeah,
Are
just
you
send me.
in office hours right now?
Yeah.
Okay, I'm starving. I have to go eat.
Then just come, and then come when you're done.
I have tutoring tonight at 6.
Oh, really? I'm a better tutor.
Well, I need your time.